And then if we would do mass spec, it probably wouldn't work because it would work because this one would cut off at the alpha carbon, which is this one. And for this one, the alpha carbon wouldn't be this one, it would be this one. So
you're talking about looking at the fragmentation patterns.
yeah, but
that's
it's still
right.
the same, right?
Now, remember we said there was an easier way to use mass spec. Remember that the parent ion in mass spec just tells you the molecular weight, but these have two different molecular weights. So in this case, we don't even have to bother looking at the fragmentation patterns, although I think you're right, you could also tell the difference between these based on the fragmentation patterns. But just by looking at the parent ion here, we would know that the parent ion for one of these has a different weight than the other. Going back to proton and MR, we said that the aldehyde would be absorbing in the 9 to 10 region. By the way, it's good to know, how about alcohol hydrogens in proton and MR? You guys remember anything about alcohol hydrogens in proton?
Is it around 6?
Now, these are a little bit weird. As I recall, these can be anywhere, from 0 to 5, something like that, but they tend to be broad, spread out because of hydrogen bonding. So if you saw kind of a broad peak, I believe, between 0 and 5. So actually, this is not too helpful because it's hard to predict where an alcohol hydrogen would be. This is not too helpful because it's hard to predict where the alcohol hydrogen would be, but we know pretty much for sure where the aldehyde hydrogen would be. So that would be much more useful to us here.
Okay.
Maybe the most important thing we got from this is learning proton NMR for aldehyde hydrogens between 9 and 10.
Yeah. Let's see the next one. The next one. It's an ether, right?
Part B.
Yes. So here we have an aldehyde. Just kidding, it might not be in there. You can.
Which one? No, this one's a ketone and that one's an aldehyde.
No, we just.
Because this one is surrounded by 2 C's and that one has an H.
I know, but I mean, like, when we're trying, if it had H's, it would have been. But yeah, it's a ketone. You know, yeah.
If it had H's, then it wouldn't be an aldehyde.
No, like this carbon had like H2 or H1, and the O might be in the middle. It'd be,
Right.
you know, like that. But since there's no H's there, we know it's a ketone, right?
Right.
And if you remember from lecture, ketones and aldehyde have different IR spectroscopy. So we could do infrared.
Slightly lower.
Yes. Aldehydes are at 1735.
Well, that was like 1715.
Yes.
I didn't have that memorized. There's a different IR for aldehydes and ketones?
Yes.
What was the difference?
1735 for aldehydes
Mm-hmm.
and 1715 for ketones.
Okay. So that would be a way to use IR spectroscopy.
Would the H's from the aldehyde and the H's from the ketones have different?
Yeah, one particular
Well,
H is
obviously,
useful.
yeah,
Which H should we focus on?
the H of the aldehyde.
Yeah, and what do we know about that?
It'll
It's
be
9 to
9.
10.
Yeah, and what type of spectroscopy is that?
H and MR.
Yeah, we could use the proton NMR and look for that 9 to 10 absorption again. That, I think, is the easiest way to tell the difference. Because after all, the IR absorptions are pretty close to each other. Sometimes if you're looking at a printout, it can be hard to see exactly where they are. So the most reliable way to tell the difference between a ketone and an aldehyde is to look for that very distinctive proton NMR absorption in the 9 to 10 region. That pretty much settles it right there.
Wait, for these questions, do they want the one best way or like always?
The answer key there, they're kind of trying to go through all the different types of spectroscopy and use the best possible approach. I mean, they're going through each type of spectroscopy and looking at how it can be most helpful to you.
So,
but it's also good to ask yourself for which of them would be the most useful. And
like,
here I think it would be the proton.
so
NMR.
like to get it like 100% correct, would you have to then say which one is the best? or just say all of, you could do this to do this, and use this to do this?
Right. Well, this particular question didn't ask you which is the best, so I guess I would give you full credit if you just went through each of the types and described how to use it. But you should prepare yourself. You might see a question on the exam that did ask you which is the best, so that would be a good thing to look at too, although that's a little bit of a judgment call. Okay.
Okay.
So again, the big thing here is to watch out for that proton NMR absorption from 9 to 10.
I think we can do C and D on our own, just because we should get to things that we don't know, just because we did two of these.
Yeah, so, okay, but we don't need to do carbon 13 and mass spec for this one?
Let's see.
Carbon 13s, they have the same carbon, so that probably would, I mean, mass spec would.
Is there a difference in the absorption between, for carbon 13, ketones and aldehydes? I don't have that memorized, so.
It's in my notes, let me see. No, there's just a carbonyl.
Yeah, in the answer key, they didn't use carbon 13. So,
It's just sort of the carbonyl, like, we should know that a carbonyl is 200.
right.
But that's, there's no different.
Okay, so for this one, it's only IR and proton.
Yeah, I mean, if you had to use carbon 13, you probably could figure it out based on the fact that here, these two are probably going to be shifted to somewhat higher absorptions because they're next to the carbonyl. Whereas in the aldehyde, there's only one carbon that's right next to the carbonyl. So that would probably affect the absorptions. But certainly it's a lot easier here just to use the proton NMR. In the answer key, they just use proton NMR for this one.
Okay.
Okay, so then let's go on to other stuff.
Okay.
We can do this. The next exercise he assigned was exercise 6. Rank in order of increasing favorability of hydration. What does it mean? Hydration. Basically, add a proton.
All right, so there's some stuff here that we'll have to talk about before we can get into this problem. This is some important material. So let's review what we talked about previously about nucleophilic attack on aldehydes and ketones. We saw that there was the 3 different categories that we have here. Now, here we're using a aldehyde or a ketone again. And they mentioned that we're going to use hydration. So what would be the nucleophile, do you think, for a hydration?
Water.
Water, that's right. So when they say hydration, what they mean is attack of water on an aldehyde or a ketone. This has to be either acid or base catalyzed. This is a reaction we didn't talk about last time. So first of all, we should just go through the mechanisms for this. So we can start with the acid catalyzed approach. Say if we have sulfuric acid, water, and the ketone. And the first thing we need to ask ourselves is this going to be category 1, category 2, or category 3? And that basically has to be memorized. Now would be a good time to take out the handout so we can see where we are on that if you guys have those with you.
Page 24.
Water and the ketone.
I think it would be category 1.
Let's see if we can confirm that. So let's look at the category 1 nucleophiles and see if we can find water in there.
It would be category 1.
Yeah, so if you look at the first page.
Acid and base catalyzed, and we said we would go over that later.
Right. Yeah, so your guess was correct. Here on page 1 of the handout, water, acid, or base catalyzed is a category 1 reaction. What is category 1? It means that a single nucleophile attacks once. So this is the simplest type. We're going to have a single nucleophile attacking once. Last time we talked about how we could do that with a Grignard, how a Grignard would attack once. But that was not acid catalyzed. So now we need to go through the acid catalyzed approach. Well, in some ways, though, this will be similar to the category 2 reactions we did last time. So let's see if we can come up with a reasonable mechanism. And we can kind of use the category 2 that we went over as the basis. Let's start going through the arrow pushing mechanism for that.
Is it equilibrium or no?
Yeah, this is an equilibrium reaction. That's right.
So first we